Alison. So I will be talking about two computers, or Piz Daint and Piz Dora. And I will claim that we are talking about the productive and heterogeneous supercomputing infrastructure for science. And the emphasis is that I hope by the end of the talk I will have to convince you that we should not worry about individual computers anymore, but about the platform on which we deliver services, and in this case scientific computing services. So I will start where basically we left a year ago, when I gave in the same theater but in some different city a talk about Piz Daint, which was the first beta-scale computing system in Switzerland. It's a Cray XC30 with 5,272 compute nodes, each compute node having an 8-core Xeon E5 CPU, so centrifuge CPU, and one K20X GPU. And you just heard that, at least I think the previous talk was on HPCG. We have a pretty performant system. On top of that, it has a fully populated Dragonfly. So the system is designed so that the global bandwidth matches the injection bandwidth that we have per node. So we did not try to save money on the network. That is one of the emphasis of this machine. Probably the most powerful network that we have available in the world currently. It was developed with application performance in mind. So it's we had a series of applications that we used in studying different architectures, and basically started with somewhere around 10, and we then down selected to 5 codes: CP2K, a quantum chemistry code; Cosmo, a regional climate code; SpecFem, a seismic code; Chromax is a molecular dynamics, and Quantum Espresso is an electronic structure code for material science. Then, once we basically decided on the architecture, we used 2 of these codes that are at different ends of the spectrum in terms of algorithmic motives and performance requirements, namely CP2K, this quantum chemistry code, and Cosmo, a version of Cosmo that we were developing in Switzerland, to basically co-design the system. So these codes were co-developed together with the system as it was evolving. We had the final upgrade a year ago in October 2013. We were in acceptance during supercomputing, and that was completed at the end of December. We had early science runs in January through March, and it is in full production in the user program since April 2014. And so, you know, the first 2 applications that ran at scale were climate and quantum chemistry. And so this is where a lot of people are skeptical. You know, you have a GPU system, and you know, you're using that as a stunt, and you know, you're not running code, complex codes. And this is a regional climate model. Here, a study of a storm going over Europe that went over Europe in 2007. This is just a demonstration, but it is used in production with this very high resolution. So you have a grid several thousand by several thousand kilometers and a 2-kilometer resolution. So we have more columns in the simulation than we have pixels displaying here. And you can see very beautiful you know, the sharpness of the fronts, the precipitation, different clouds, the way the weather systems emerge in Europe, the role that the Alps play, and so a number of things. So I'm not a meteorologist and cannot go too much into the scientific detail. The code itself was co-developed by us at CSCS Supercomputing Systems, a company, and Meteo Swiss. And scientists at ETH Zurich. Then the second big application that ran was CP2K, quantum chemistry, And the example, or one of the first results, was the ability to properly reproduce in an electronic structure simulation the phase diagram of water. So put in simple terms, the question, does ice swim or sink, in water? This turns out to be, it's a simple thing that we all have experienced, but turns out to be a challenging thing. And the challenge to get this result right is because ultimately what we have to solve here is what is called the many-body Schrödinger equation. So it's a quantum many-body problem. From a computing point of view, it's an NP-hard problem. So as we increase the number of particles, number of water molecules, electrons that we have to simulate, the computational complexity goes up exponentially because the dimensionality of these operators of the Hilbert space increases exponentially with the size of the system. So that is a bad proposition for computing, normally. And so in chemistry and material science, we have something that we know as local density approximation to density functional theory that pretty much simplifies this equation by making some approximation on how the electrons interact with their surroundings. And this turns out to be a very good theory for many cases, but it will give you the phase diagram of water wrong. So the ice would sink. And you have to, and then there is something by John Perdue, a well-known chemist and electronic structure theorist, actually who works and lives in Louisiana, in New Orleans. He defined this ladder of approximations that you can improve the approximation of this equation, and you have to go up basically 5 rungs in this ladder. So the typical runs that hybrid functionals use on machines, like there was a big paper from Tianhe 2 that would still not get things quite right, and you have to really go to this Möller-Plosset perturbation theory, MP2, to get the results right, and that's what van der Wondele and Hutter implemented and ran. And to give you a feeling of the problem they are up against is, so we have water molecules, and in water itself and then in ice, these molecules interact through hydrogen bonds that form between the hydrogen atom and the oxygen atom. And this is what is called a van der Waals interaction, which codes like Gromax parameterize, and we are trying to get out of first principles here. And the energy scale of this interaction is about 6 orders of magnitude smaller than the energy scale of the electrons inside of a molecule. So unless you get computations accurate to this level of accuracy and right, you will not get things right, and the ice pair will sink. Not because the ice melts, but because the ice sinks. So that's roughly the scientific accomplishment. This is showing how this code scales on different machines. So we are comparing Piz Daint and Titan, and on Piz Daint we're running on CPU only and hybrid CPU GPU. So this is for different system sizes the number of simulations per day. If you do MD or Monte Carlo, you do many of these in sequence. So this is 64 water atoms, molecules, 256 and 512, again for the electronic structure specialists here, in calculations per day for this system using MP2 theory for the correlation part, exchange and correlation. And you can see here the jobs running on CPU only, running hybrid on Piz Daint and running on Titan. And you can see that something that we see often in jobs running on GPU when we do strong scaling. So given problem size go to more and more nodes, at some point the CPU only jobs start winning. So the cost of spinning up kernels and running things on the GPU becomes higher than the benefit from the GPU, and that is at that point the CPU only runs start to do better. Okay, basically a different way of putting this is you don't have enough work to hide the latency, which you have to do when you program on a GPU. Or in this particular specific case, the matrices you're multiplying on the GPU become too small. But you can see that Piz Daint is actually doing rather well when run in hybrid, even compared to Titan here. So even the biggest problem we can run almost, say, at half the speed of Titan when you go to the full size of Titan. So we are very happy, and you saw this also with the HPCG benchmark. Another problem is the bonsai code, so an n-particle gravitational interaction code, which is one of the Gordon Bell finalists, and I recommend that you go to this presentation tomorrow, so you will get the full story behind this. The particular reason why I show this is now a visualization. When you go around the corner, you see similar images, but the difference is over there you have the simulation running on Piz Daint while you're looking at the image, and then the rendering is happening on the same system, the same GPUs, and then the images are streamed over here, and you're looking at them, and you can interact with the simulation over there. Okay, so this is basically a first step in the direction where we are going, that we want to move these systems from being pure simulation system into systems that integrate visualization and data analysis. And so this was the first of these, I would say, rather exciting runs. You see here how the galaxy started homogeneously, and then over time in the simulation these arms develop and the core in the bar, and so these are emergent behavior of gravitational systems. And as I said, you will can hear the expert talk about this tomorrow in the Gordon Bell finalist session. I think this one was running on 1,000 nodes. I don't know what they were rendering on, somewhere around probably a few hundred nodes. Peter Messmer is here, who knows all the details about the visualization. Now, another step in this visualization data analysis saga is one that John Biddiscombe, who is at CSCS, put together. The previous one, by the way, putting together the system was Gilles Forestier and Peter Messmer. Here it's John Biddiscombe. This is a brain simulation. We are hosting the Human Brain Project Development System at CSCS, and here you see this. Basically, the difference between this one and the previous one is this is running on standard ParaView software. So standard software that you can even run on your laptop. And you can see here the decomposition into different nodes. I think this was running the visualization on 100 nodes. Somewhere around several billion of tetrahedra. Way too much information for somebody to look at, and what they are doing here is basically they run the rendering on OpenGL, and on the same GPUs they do the ordering of the sequence, depth ordering of the tetrahedra using CUDA. So the sorting mechanism is done with CUDA, and this is pretty much done almost in real time. So you could see how they are moving around the images, and the rendering, the ordering, everything is happening at the same time. So it's a very powerful visualization engine and data analysis engine. Then we roughly, our user program at CSCS is somewhere around 90 projects, 400 users in the area of climate, meteorology, material science, mostly electronic structures, so quantum simulations, life science, a lot of molecular dynamics, NAMD, AMBER, GROMACS, geophysics, physics, you saw the astrophysics simulations before, engineering and energy, and the new domain, since we are partnering with EPFL on the human brain and blue brain project is neuroscience. We are open as a user program, of course, to all Swiss scientists, so from all universities in Switzerland, as well as a number of research institutes run. Meteo Swiss runs a separate system, and this is what I want to stress here, we also have, the system is open internationally, and we have currently about 10%, and this is growing rapidly, of our projects are international, so from users like Zwart from the Netherlands or people from the US and Europe and other parts of the planet. So an overview of the services that we provide. So because I want to take you away now from the machines and focus on the services. So we have the user lab, which is pretty much the user project I've been showing up to now, belong to this open peer-reviewed access, similar to Insight or the Piz access in Europe. And it has several supercomputers and a data storage and analysis platform with, again, a number of computers and storage facility, as well as a number of application development projects that we take very seriously in Switzerland. And then we have other services. We have this Blue Brain machine, a BlueGeneQ system, and active storage research, so BGAS research that we are doing with IBM and EPFL. We have the Meteo Swiss, which is a high availability system running weather forecasting. We have the Swiss Institute for Particle Physics. So this is the Swiss part of LHC data analysis that is running at CSCS. We have a number of clusters that are either hosted or housed at CSCS, and we have cluster services, and this is the new part that we have integrated into Piz Dora, into one of our supercomputers. So we can currently support clusters separate, but we also started to integrate these services into the main machines. And we also, that's the last point here, a data analytics platform that we are developing also on our supercomputers, and we run some industry projects as well. So you saw in the previous slide a number of places where this computer Piz Dora came up. So what is this? Well, it is basically an addition of additional cabinets, XC cabinets, that we have here the 3 rows of Piz Daint, 28 cabinets, and behind this we have this row of Cray XC40, currently 7 cabinets, could be expanded in the future, that will replace our previous flagship system, Monte Rosa, which is a multi-core system. It is a replacement for all our pre- and post-processing systems. So it has fat memory nodes and that are included here. So we do pre- and post-processing, and we have these number of cluster services. In particular, we have the University of Zurich and Paul Scherrer Institute that have moved their clusters to CSCS, and they are integrated into this machine. So rather than having a commodity cluster, it is part of a large supercomputer. Then Piz Daint has 28 cabinets, and the things I talked about is computing at scale, petascale system, and integrated the visualization is part of the system, and we can run both at the same time. So what we are looking at is really no longer 2 machines like we are used to, list machines on top 500 and so on. What we see is just a platform that is heterogeneous, has CPU, so dual socket CPU nodes, multi-core nodes, and has CPU, GPU nodes. Yeah, that should be a GPU here. A mistake one shouldn't have in an Nvidia booth on the slides, so I need to fix this. Where we do compute and visualization, Then we have large memory nodes. We have these SSE-based I/O burst buffers. I don't know, Cray has a different name for this. Data warp, yeah, exactly. We have a very low latency network and this very high bisection bandwidth that I stressed. And now you can ask, well, isn't this expensive? You know, waste a capability system on cluster services? It turns out no. It turns out it is more economical to do this way for various reasons. But the one thing that is very attractive for doing this way is both from the point of view of the scientists and from the point of view of the business that I have to run at the center. From the point of view of the scientists, they basically can do their entire workflow, including the visualization, on the same platform. They don't have to move data around, and in some cases you don't even worry anymore about I/O, because you can do the rendering while things are live in the data, and so you can look at the data in a totally different way than you can if you have to output, wait until you read in again, and so on. So this is very attractive to the scientists. It is also attractive for those who are developing. Say you develop a code on your laptop, then you move it to a cluster. But here the cluster happens to be the same machine that is then your capability system. So it's very efficient to move your development flow through the system. And finally, for us, or for when we run the business, we can now easily add services without, we can elastically expand the platform or, shrink it. Well, we hope we don't have to shrink, but we can continue to expand. And previously we would have a new service, would be a new system. We have to hire new people. Things would be much more complicated. So this is a very attractive also for the business model of the center. And that's where I want to leave it. Thank you for your attention, and I'm open to questions.